Okay. Hello, everyone. Thank you all for coming. Hope you got your pizza. My name is Charles, and today I'm going to reveal the future to you, or at least predict it, because no one can really reveal it. All right, so this talk is called The Proof Must Go On, Formal Methods in the Theater of Secure Software Development of the Future, because I couldn't think of any shorter title that would convey the same meaning. This is actually a presentation of an essay that I wrote and published in Splash, which is a conference regarding the science of software development. And they have this track called Onward, which is typically about, I guess every submission to Onward has something special about it. It's got maybe a weird format, or it's a personal anecdote that has some kind of at least pseudo-scientific meaning to it, or you're trying to tell a story. And what I did for my submission was throughout the study of my research and of my study of the history of computer science, I have noticed some overarching patterns in the directions that funding and manpower go. And if you know the way that money and manpower are flowing, then you can probably guess where money and manpower are going to go in the upcoming future. So that's what this talk is all about. This is actually going to be mostly a history talk, and then we're going to get to the future right at the end. And I know what everyone's thinking, ew, history, which is why periodically I'm going to ask questions, and people who answer them get a Pokemon card. So I think that's one way to keep everyone involved. Yeah? All right. So just some quick precursors. Oops. So first of all, let's talk about trust and what does it mean to trust software. So trust means that we are confident that software is going to behave the way it's supposed to, or the way that we think it's supposed to, right? We want code to be reliable, which means it shouldn't crash all the time. We want it to be secure, so it's not going to leak secret information, or it's not going to allow an attacker to gain access. And we want it to be correct. We want it to fulfill the purpose that it was written for. Of course, the amount of trust that you have to have in your software is going to vary very greatly across different contexts and different applications. Of course, I don't really care if my website login page crashes 1 out of 100 login attempts. That's annoying, but it's not the end of the world. But if 1 out of 100 autopilot softwares crashes the plane, I probably wouldn't ride on planes anymore, right? So there's different levels of trust that you need to have. And then something pretty critical is that you often don't realize you're trusting something until the trust is broken. So for example, I would say that probably 90% of people who fly on planes don't think about the fact that there is software running the autopilot. Or maybe that there's even autopilot at all. Maybe they think the humans are in the loop the whole time. Because it's just not in the human nature to think about every single worst case scenario that's going on. So a lot of times you don't notice exactly what you're trusting until you can't trust it anymore. So who needs to trust software? Of course, the users of these critical systems. That includes if you have a bank account, you need to trust their software. You need to trust your hospital's software. Of course, the government needs to have some amount of trust in its software. But everyone in here who's writing code, you are trusting the libraries that you import. You're trusting the compilers that you use. You're trusting the operating system you're running your code on. You're trusting your browser. You're trusting everything, because you can't really live in a world where you don't trust anything unless you're going to write your own software, but then you're Terry Davis and you die of brain damage, right? So that doesn't really work. Correlation.
That was correlation, not causation.
Yeah, maybe. Society at large just relies on the trust of infrastructure. It's like a core human belief, and so you can't really do without it. And finally, just another bit of details. So you saw that there were formal methods in the title of this talk. if you've seen me talk before, you probably know what formal methods are. If you haven't, formal methods is this big category of approaches towards security where you typically do some kind of mathematical verification that some code is correct. That could look like writing a proof that for all possible inputs to a function, the function's output meets a correctness specification. Or you could say, I'm going to throw my code into a model checker, which is going to do this like big state space exploration, and it's going to find all of the bugs I've got in it. Something that's formal methods that nobody thinks about as formal methods is a type system. In C has a type system. It's not a great one, but it works. Of course, functional languages have very strong type systems. Java has a type system. Every language you're working with has some kind of type system. This is a formal way for the compiler to reason about your code and to help you write better code. Formal methods are mostly academic until I'd say the past 10 years or so, when they've started creeping into industry more and more. And again, the main idea is that we want to just reduce bugs, reduce security vulnerabilities. We want to have assurance, not just trust, but assurance that the critical systems that we depend on day to day are not going to kill us or lose all our money or lose our social security number, whatever. Okay. And I should mention, actually, before I talk about the past and the future, I want to give you all a bit of information about my lens as a person about how I look at the past and the future. So I am a formal methods researcher. My lab writes proofs about binary code because the binary code is where all the sausage gets made, and it's the most complex, so it's got a bunch of space for bugs in it. So when I look at a piece of code, I'm typically looking for how it can go wrong and how it can do something that maybe the author didn't intend it to do. I am not a huge fan of artificial intelligence, but I think it's a pretty good tool for a lot of things. I think that's going to have some impact on my lens. I don't know. I think those are some big things. Does anyone have any questions about my literative lens of the future?
How is what you do different than just like someone who's like thinking, well, how do I get rid of all the bugs in this program?
Yeah, that's a really good question. So I didn't really cover it a whole lot in this slide, but when it comes to formal methods, you're right. You absolutely can just take the mindset of, well, I'm going to stare at this code really hard until all the bugs are gone. I'm just going to keep modifying it until all the bugs are gone. There's two issues with that I see, two big issues. The first one is pretty straightforward. It's that people don't usually write assembly. Or I should say, people don't usually write machine code. At the very minimum, they are writing a text file that is going to be compiled or assembled or linked or in some other way put together by another piece of code. And so if I'm writing a piece of C code, I can be sure as the sun's going to rise that there's no bugs in my code, but I put it through a compiler that has a bug in it. Ta-da, my code has bugs in it now. Like maybe the compiler has adjusted the semantics of my program, and all of a sudden, the thing that I was very certain had bugs in it doesn't have bugs in it anymore, or doesn't have bugs in it now has bugs in it. And the other reason is that formal methods does not involve just staring at code until you're sure that it has bugs in it. We have these things called interactive theorem provers. This bird logo is for a theorem prover called ROCQ, R-O-C-Q, in which you can write programs and you can also write correctness specifications and proofs that code follows those specifications. And the way that the language checks your proof is identical to the way that it checks types. So if you can trust that your compiler, your Java compiler or your C compiler is not going to change the types of your code, then you can also trust that the ROCQ compiler is going to maintain the veracity of the proofs that you write when it says that you actually wrote the correct proof. It'll tell you if the proof is wrong, and it'll tell you if the proof is right. What's up, Marty?
So you mentioned there a mathematical underpinning behind this whole method so that
Yes.
at the same time you can have a mathematical proof by writing the only verify code with that same level of trust?
Yeah. When I said that the way that the proofs are checked is based on the way that a type system works, I mean that for the past 100 years we have figured out how type systems work, and we've figured it out to a point where we can write the type checker for this proof system in approximately 50 lines of code. And then you can have 1,000 grad students pore over those 50 lines of code, and you can have, the assurance that the only part of the system that you have to trust has been hand-checked by 1,000 mathematics and programming language specialists, graduate students over in France, where they love this kind of stuff. So if you can trust the French, you can trust the proof. All right. So that's enough about that. This is a separate talk that I will give probably next semester. I love giving the talk of why you should trust the proof checker. But let's get into history. So 100 years ago, we're back to the 1920s. Actually, let's go 120 years ago. There was this mathematician, Hilbert. He was a big famous guy at the time. Don't really worry about what he did. But he proposed this list of questions that is referred to as Hilbert's program. And these list of questions, they would ask, about the nature of mathematics and physics and reality and truth and philosophy. They were all like really, really deep philosophical questions about, what it is to exist and what it is for things to be true. But they all had pretty real applications to mathematics at the time, because just 10 or 20 years prior to him asking these questions, we had invented this thing called set theory, which took the math world by storm. And then we found that there were bugs in the assumptions of set theory. So we had these axioms that laid out the core operations and the core relationships of set theory. And it turned out that those axioms were inconsistent. So we had, every mathematician in the world was obsessed with this great, framework for reasoning, and all of a sudden it all comes tumbling down because we hadn't spotted that there was this reasoning flaw. And so we ended up with questions like, what kinds of things can we know? And under what conditions can we know them? And if we have a mathematical proposition like, for all numbers n times 0 equals 0, how do we know these things? How do we prove these things? How do we determine if they're true or false? And again, I can't get too into this, but the answers to these questions involved the invention and discovery of computer science. And with the invention of computer science came formal programming language theory. So this was, here's a Curry, Church, and Turing. Turing, he made the Turing machine, which is the foundation for the von Neumann model, which is what every computer in here is running on. Church did the lambda calculus, and the lambda calculus was isomorphic to Turing machines, so they can both do anything the other can. And Curry did some prior work on another kind of computation framework. But the thing I'm trying to get across here is that these three people, of course many, many others, basically invented computer science because they wanted to solve a really perplexing set of questions about mathematics. And what happened next? After we've got all this theory that was, locked up in the academic institutions, what good does that do anybody, right? Well, the government thought it would do something good for them, and so when the war came around, World War II, that is, the government decided, let's put these eggheads to use and make them build machines for us that'll calculate our ballistics trajectories and crack German ciphers and do administrative tasks for us, because we're the only guys with any money or enough money to build, these enormous machines that might not work, really. It's research, right? So uh, straight from academics into the military and the government. And it wasn't even until after World War II that anyone thought to use an electronic computer for science or business or anything like that. Just nobody had thought of that. And it wasn't until the 50s or so that more of the big businesses had some kind of computing structure inside of them. And so what happens next? Computers get smaller. And because they get smaller, you can fit one of them in a regular room. And eventually you can fit multiple of them in a regular room. And then you can put people in front of them, and the people tell the computers what to do, and now your business can do more things. Pretty straightforward, right? That's like kind of how it works. So as you know, hardware costs went way down. But I said that like these humans tell the computers what to do, but they had never done that before because software wasn't a thing that like existed yet. And so what do you get when you have an unstructured way of doing something? You have a lot of bad somethings that come out the other end. So with all these software developers who had never been trained to write software, they were mostly electrical engineers, you ended up with a lot of bad software. And you know, the government discovered around this time that they discovered the same problem we have now, which is that typically software projects come in over budget and underdeveloped, meaning they don't actually do what you want them to do. They cost a lot of money, and they cost too much money. So we have this problem of how do we stop developers from writing low quality and unmaintainable code that doesn't actually do what we want? And the solution that academics came up with was, let's just reason about the code. Let's like invent tools for thinking about code and automatic processes that can step through code and figure out what's going on. And here we are in the 60s and 70s, where we invented things like denotational semantics and horologic and the weakest precondition. I think for the undergrads, probably the weakest precondition is the only thing that you'll understand if you've taken PLP. But basically, these people, you know, some of these people are still alive. They invented the groundwork for reasoning about programs. Who can tell me what happens next? Like immediately after this, like who is going to utilize the developments of formal reasoning about programs? Huh? The government, yes. You get a Pokemon card. Everyone just come up after, and I'll hand out Pokemon cards then. Yes, so, okay, these two slides are backwards. I'll go in that order. The government was the ones, they were the ones who came and said, it's so great that you figured out how to be certain that software is doing the right thing. Now we're gonna make you do that for us. And so, you know, eventually the Cold War stops by, and now we have these software-guided missiles, and we want to make sure that the missiles don't like crash on U.S. territory when we launch them against the Russians and the Cubans, whoever. And so DARPA funds things like the Ada programming language. Has anyone heard of the Ada programming language? Okay, so a lot of people have heard of it. Has anyone actually written any Ada? No, I don't blame you, because like nobody uses it except for DARPA, basically. But basically, Ada was a product of the Algol 60 family, which also produced things like Pascal, if anyone's written any Pascal. And the whole idea was like, we want to build programming languages in a principled way that allows us to do this like formal reasoning about them, because if we can reason about a program, then I can reason about the software in the missile guidance system, and then I can make sure that this thing's not going to crash where it's not supposed to. So again, academics had a problem, the government had, or society had a problem, academics had a solution, the government wanted to use it. And then I kind of glossed over this, but for the last part, but the next thing that happens is industry adopts all of these practices. And then what happens when the industry needs something? all of the universities are going to say, well, I'm going to train my students on what the industry needs, because the job of a university is to, create valuable members of society, or, I get, maybe there's some contention on that statement, but like, kind of generally, that's what they're supposed to do in my mind, at least. And so by the 70s and 80s, formal methods and these reasoning tools that academics had invented became common in all of the regular university curriculums. So students were expected to be able to do program analysis. Has anyone in here written a proof about code ever? I see approximately 10 people, and most of them are in Dr. Hamlin's language-based security class. So yeah, not very many, right? So why, can anyone answer, why are we not educated on that anymore? Can anyone predict the next big problem that society has? No. This is it's incredibly difficult to do advanced program analysis, as these 10 people will tell you. So you can't abstract it away. But so can anyone think, like, we're in like the 70s, 80s, what is like the next thing that happens with computers and society that introduces a new problem that we have to solve? You raised your hand for a second, you put it back down.
I was thinking that maybe companies wanted more just code monkeys instead of computer scientists.
Exactly. So 80s, 90s, now we have companies whose entire business is computers. We have companies who only sell computers. Before, it was like all of the companies who did sell computers used to do other things before. But now we've got companies that only sell computers. For the first time, we have companies that only sell software. That was a new thing. That didn't really happen a lot before. So yeah, society had this new problem where it's just not enough to write good code anymore. We just need people who will write any code, because any code is progress. Screw the consequences, whatever. I just need someone to write my 10,000 line website because the internet is new, right? That was like the whole idea. And so here we are at the turn of the century. Yeah, so good. You get a Pokemon card. So we've got this, this new problem where, students are now just going to be taught how to write code. And there's an incredibly good letter that Dijkstra wrote to the UT funding board or something. I'll pull up a link after. Basically, the UT system had decided we are going to replace our freshman Haskell class with a freshman Java class. And I think probably half the people in here took a freshman Java class, or maybe a freshman C++ class or whatever. But Dijkstra writes this letter to UT saying, like, I tell people that, or people ask me, like, why are you in Texas? Isn't it like weird and conservative and backwards there? And Dijkstra's like, well, it's actually not that bad in Austin. We even teach Haskell as an introductory programming language. And his reasoning for why Haskell should be around is like, it teaches you in a way that imperative languages don't, how program correctness works, and just the structure of defining like a mathematical relationship between inputs and outputs. And this is like such a different way from the like procedural way that we write code in C or Java or whatever. So anyways, that's a really good letter. I'll pull it up in a bit. But we're at the turn of the century. We're in the early 2000s, late 90s. And this field of program analysis has started to split. Or I wouldn't say started to, it's already split, actually. We have these like formal methods that I've been telling you about, like proofs and model checking and type systems and whatever. But then we also have what I'm calling like programming techniques. And I should mention that these aren't like two like completely separate camps. Of course, a lot of the same people work on both things, and there's lots of overlap, whatever. But there's two big categories I see, where these programming methods and techniques are things like a better IDE, or software model checking that you can apply en masse, where you don't have to set up a lot of tuning parameters, or unit testing frameworks. Like they had been around, but they weren't like widely adopted for a while. These are all things that you can give to a programmer who doesn't have like a formal education, and the programmer will know how to use it. Maybe model checking is maybe an extreme case of that, but I think even anyone in this room, anyone at regular company, doesn't have to be Google, whatever, could understand software model checking and at least how to use it, if not the like foundation of why it works. But at the same time that all of this stuff is going on, formal methods is still going on in the background, and formal methods is still attacking this problem of like code quality or code correctness or like the things that the industry and therefore education have kind of abandoned. But the government hasn't really abandoned it because, of course, the government still has missiles and they still have drones, they still have airplanes, and they still have like power plants and things that need to be correct. Absolutely, right? And so around this time in the early 2000s, we see things like separation logic, which was an extension of Hoare logic. So it's another kind of reasoning framework for reasoning about imperative code. But it'll let you reason about like memory and what memory is in scope and what memory is accessed. And so you could write things like, this program has no illegal memory accesses in it. And of course, I think we all know that like memory access is like the hardest thing to figure out for a complex low-level system. It's like, of course, you're going to have null pointer dereference bugs every once in a while. You have things like certified compilers. This is insane. There's a compiler called CompCert, and it's a C compiler, except it has included in it a proof that any C program you give it, the semantics are going to be maintained between the C and the assembly that it compiles. You don't get that with GCC. You don't get it with Clang. You don't get it with any other compiler because it took 100 people 5 or 6 years to write this thing. And it was incredibly difficult, and it was a huge, huge development. And of course, half the people in this room haven't heard of it because it's not free for use. You have to license it if you want to use it commercially. What an awful decision. I can't believe they did that. So I just want to bring up that formal methods is still working in the background because at least the government still has these needs, but industry has decided, you know what, it's not profitable to keep doing all this program analysis, so let's just write more code. Actually, I hope no one looked at that slide because now I'm going to ask a question. What happens when the industry has that opinion about development? Industry has decided program analysis is not profitable. We will not do it. We want people who can just write code. We need, huh? Yeah, the industry won't fund program analysis, but what's like the negative consequence that's going to happen to society?
Doesn't this scream like lack of quality control or something?
Yeah, but what happens when you have lack of quality control? No, you're an officer. You don't count.
Code gets worse.
Code gets worse, sure.
I was going to say that the people looking for those jobs are going to adopt the same viewpoint.
Not really. I mean, kind of.
There's more vulnerabilities.
Damn it. Okay, you already got a card. You get 2 cards, I guess. I'm sorry, y'all. But okay, all right. Yeah, give the card away.
Security issues?
Yes, security issues is what happens next. I think everyone here probably knows that security wasn't a problem until like 15 years ago in the eyes of a ton of industries, industry groups. Like nobody really gave a second thought about cybersecurity or making sure that code was safe. Like it's kind of a recent development in the past 15 years. It does. Yeah, CompCert is not owned by INRIA anymore. It's owned by a company called Absent. I actually don't know, and that's a good question. No, ABSINT. Yeah. Yeah, so the industry has adopted this idea that we just need people to write code, screw the consequences of bad code because we'll just write more code on top of it and then we'll be safe, right? And of course, that leads to all of the vulnerabilities we know and love today. And this leads to academics targeting cybersecurity. All the formal methods people who, I don't know, I wouldn't say that, I would say for formal methods, cybersecurity has been like a focus for basically its entire existence. It's much more focused now, in my opinion. All the formal methods researchers 10, 15 years ago kind of just decided that most of our work is going to be about like cybersecurity for critical infrastructure. And so all the academics decided, let's solve this problem. They start solving the problem. Then the government says, hey, it's great that you're solving this problem even better than you were before. We'll keep giving you money. We'll give you more money. We'll open more projects, and we'll give you more money for those. And just like formal methods gets bigger and bigger. And then, of course, industry after that says, look, the government did it. All right, now we're going to do it because, oops, we got hacked 100 times, and everyone's login information is public now. So now they do have a reason because they're starting to get sued for, these class action lawsuits of, you didn't protect my my information, and you should have. That's kind of your job. And so yeah, that's we've seen the pattern how many times now? Like 3, 4 times. So yeah, I'm gonna go over where we are right now, and then I'm gonna ask a big question. So everyone, listen. So where are we right now? We have all of these tools for cybersecurity and for formal methods. We have certified compilers, model checkers. We have formal verification systems. We have linters. We have just so many things for any combination of manual and automatic effort that you want. We've got a tool for it. We're still not at this like full adoption level. It's still really expensive to do formal methods on a large scale. It's really hard to train developers because developers never learned how to do this because it wasn't profitable at the time for developers to know how to do that. It's expensive to rewrite software. It's expensive to replace software. But again, all this adoption is being driven by cybercrime, which costs more and more every year. I mean, it's almost an exponential growth. It's ridiculous how much money companies lose to cybercrime. And then one thing I'm seeing is that formal methods courses are very slowly returning to undergraduate programs as electives. Anyone who's signing up for courses soon, look for, does anyone know the course number for APL that's cross-listed? Anyways, Dr. Hamlin, oh.
Like .apl?
Yeah.
A program language APL?
No, not that one.
Okay.
We have a course for graduate students called Advanced Programming Languages. And it's really good. It takes you through the fundamentals of programming language theory and a bit of the fundamentals of formal verification. It's an insanely good class. I personally believe it is the most informative class offered at UTD, at least for computer scientists. I don't know about anything else. Anyways, it's cross-listed for undergrads now, so everyone go take it. It's awesome. It's the best. And I'll be your TA, so I'll grade extra nice probably. In Minecraft, looking at the camera. I won't actually give anyone any extra points just because I'm nice, sorry. Huh? More TA hours? I don't know what you mean. But I'm just specifying to the camera I'm not actually going to abuse my position as TA to give points to people, whatever. Anyways, so somebody who has not raised their hand or hasn't answered a question, tell me what is the pattern that we've seen 3 or 4 times now?
Looks like there is a problem, someone comes out with a solution, but that solution is created yet another problem, which is then created by another solution, but then something's neglected again, and then there's another problem.
Okay, I like the first bits of that, but I'm interested in the parties at play. Oh, wait, no. What were you going to say?
It seems like the pattern starts from the government, then moves and the academics, and then the government gets involved, and then the industry adopts it because the academics do what they do really well because the government is funding them, and then the industry creates problems because they aren't actually doing everything the academics are doing, and then a problem happens, and that's solved by another group of academics which get funds, and
There you go. Yes, Pokemon card. So the pattern. I'll spell it out real clearly. Society has a problem. Academics decide to solve it. Things like Hilbert's program, that was a big problem. The issue of having like all of the code be bad and unmaintainable, that was a problem. Security is a problem. And of course, any of this research academics do is going to be years ahead of industrial use. The government then says, hey, I like your research, I will continue to fund it, as long as you apply it to critical systems. And so they apply the solutions of Hilbert's problem to cipher breaking and ballistics in World War II. They take the solutions of poor software quality and apply it to the Cold War critical systems. And then now we're applying the solutions for cybersecurity that were invented 10 years ago to the problems of cybersecurity now. And the reason the government does this, again, is because generally, they are the only source of funding that's actually large enough to take the risks on this. Because for every successful academic research story, there are probably 5 unsuccessful ones, or stories where they say they're successful, but they actually weren't, which that's really frustrating. And then the industry comes by and then says, hey, it's so awesome that the government took this risk for us. Now we'll take all the spoils and just use the stuff that works. Their adoption is going to be motivated by profitability or whatever their infrastructure needs are. Of course, they're going to wait for the results to be validated and functional. And then we've got this exception nowadays where we see massive companies actually fund some of the research now. So AWS funds PhD students at UT to do formal verification for massive distributed systems. And Microsoft funds a lot of students at UW. And yeah, some of these companies are so big these days that they have the money to actually do a lot of this research. Actually, Microsoft also funded quite a bit of CompCert, so that's interesting. Finally, education. Universities are motivated to teach students the skills that the industry needs. Of course, there's going to be some lag behind what the industry needs and what the university will teach. Looking at you, UTD. So at one point, the problem was writing correct and high quality software, and so that's what the universities taught back in the 70s. And then it was a problem that the entire industry had adopted Java, and so now everyone has to teach object-oriented programming. And we're starting to see that more universities teach cybersecurity courses now. So again, the whole purpose that a university should fulfill is preparing the next generation to adopt whatever methods are going to be useful when they graduate. So I love this diagram. It's a summary of the things that I was just talking about. There's this talk that was given at a conference I went to last year, and it was so good. It was everything that I just told you, but it was way, way more in depth if you thought I wasn't being in depth enough. And we can see that there are so many things moving between government, academia, and industry. When he went through this talk, each of these boxes was added one by one, so it really builds up. I have a link to this talk at the end of the slide deck, so if anyone's interested, please go watch it. It's such a good, interesting talk. Okay, we've finished the past. Oh my gosh, and I'm doing good on time too. All right, so if we've got this pattern, we can probably apply it to the present. And we can look at whatever problems we have today. We know that the government will fund it next year. Industry will adopt it 5 or 10 years from now. And education will adopt it 11 or 12 years after. What are the big problems of today? Vibe coding, yeah, good answer. Anyone else? Problem? Come on, complain about society.
Whatever problems AI is fucking up right now.
Yeah, okay, that's a double answer. Yep.
Currently, the big thing is AI, and AI is very expensive, so probably they're gonna have to be
Okay.
gonna make it less expensive.
Okay, yeah.
Oh, climate change.
Climate change is a problem. I'm saying it on camera.
Wait.
I'm not suicidal. Climate change is a problem.
Wait. Oh, the insane amounts of water needed to cool the AI system.
Sure, sure. A lot of AI answers, not really what I'm going for.
There's like supply chain attacks where you have to rely on the fertilizer.
Yeah? Yes. Okay. So there were really two categories of answers there. There was one about AI, and like AI is expensive and energy inefficient. Sure. There certainly are researchers working on that, and there certainly is government money funding that. But we're in the cybersecurity club, computer security group. So let's look at the security question, which is like everything's insecure still, and we've been trying, and we have 10 or 15 years of like practical cybersecurity research going on, where we have some automatic method to repair a piece of code to make it not vulnerable to an attack. For instance, raise your hand if you know what control flow integrity is. Oh man. Okay. We should give a control flow integrity talk sometime. It's super important. Okay, raise your hand if you know what a ROP attack is, return-oriented programming. Okay, so we all know, a lot of us know what a return-oriented programming attack is. Return-oriented programming is where you can utilize a buffer overflow to change the return address of a function, and now you can return anywhere in virtual memory, and you can do whatever you want sometimes. Very bad thing. Control flow integrity is an extremely robust, sometimes hardware implemented approach to ensuring that return-oriented programming attacks are mathematically impossible. Incredibly cool, practical, automatic piece of security. So yeah, we absolutely need to talk about that. Yeah, absolutely. Pointer arithmetic is a problem. I'm really glad you mentioned that because it feeds into my research. So the problems of today are that things are still insecure even though we have all of these automatic methods. These automatic methods that were supposed to solve us, but for one reason or another are supposed to help us. One reason or another, they're not. So I'm going to give you my interpretation on at least what the future of formal methods will look like, because I think this is the perfect time for formal methods to be big and get big. So here's a little timeline of what I think is going to happen. Pretty soon, I think probably next 5 to 10 years, we're going to see hybrid top-down and bottom-up verification systems. None of you know what that is. That's okay. I'm going to get to it. After that, or probably concurrently, I think we're going to see these things called minimal verified components. I'll get to that in a second. We're going to see verified standard libraries. We're going to see languages that build in support for reasoning about programs at a manual level. We're going to have to deal with hardware because every year, every month, there are a new wave of hardware attacks that come out. Ridiculously interesting things like hiding a virtual CPU in RAM at the factory, and then when you send it to somebody, the RAM stick looks normal. You plug it in, and all of a sudden there's secret virtual CPU that can look at every access and write that you do, and of course now they have complete control of your machine. And it's like so many crazy, interesting hardware theoretical attacks. Of course, we're going to see educational reforms. And it's mostly fun at the end, a little Deus Ex Machina, little science fiction. So everyone turn off your science hats and turn on your science fiction hats when I get to that. All right, so top-down and bottom-up verification, what are they? Top-down verification is the common kind of formal verification, where I write a program in Python, C, Java, OCaml, high-level language that goes through a compiler. And I have some model of the semantics of that programming language, and I write a proof about the program that I wrote in the high-level language, and then I have one of two options. I either trust the compiler, I trust that the semantics of the assembly are the same as the source level I wrote, usually a bad decision, unless you're using something like CompCert, or actually, no, those were the two options. Use CompCert or trust the compiler. And those are bad options, especially because there's code that isn't written in those high-level languages. There is assembly out there, handwritten assembly, and the worst part, it's in your C standard library. And raise your hand if you can think of a program that doesn't rely on the C standard library. Yeah, it's bad. You can't, because everything uses it. Everything's compiled with it at some point. So yeah, this is a problem. You have to reason about low-level behavior at some point. This is actually my research and my advisor's research. This is why you should take our class next semester. It's going to be awesome. Basically, so we call this bottom-up verification, where I say, forget about the high-level language, forget about the compiler. I'm going to take the binary, the thing that not even the assembly text file. I'm saying the binary, the thing that is out the end of the linker and the assembler and everything. And I'm going to say I'm going to analyze that. This sucks. It's a really hard, difficult, complicated way to do it. Why? Someone raise your hand. Tell me why. Yeah, binary code sucks. If you've ever done reversing or binary exploitation, you know it's really hard to even do like a non-formal analysis of what a binary program does. And so if one of the things is really nice and pleasant but doesn't give you a lot of trust, and the other thing is really ugly and unpleasant but does give you a lot of trust, stick them together and do both of them, basically. So I'm proposing this thing called full stack proof front end. It's going to most likely utilize something like a certified compiler to ensure that I can write proofs about the very, very high level algorithmic behavior of a piece of code. And at the same time, I can reason about low level behaviors like what is in a specific register, or how fast is this code running, or what's in the cache right now, and things like that. Things that are so low level that your language like Java doesn't even have a way to talk about it. I can't talk about registers in Java. I can talk about registers in C. It's like convoluted, but you can. And just if you have this full stack thing, then you get complete software verification, and you get it easier than you would have with binary verification, and you get it with the trust that you would get from binary verification. So that's idea number one. I think that's happening soon. Lots of people are building many more certified compilers right now. The science for building them modularly is accelerating really rapidly. It's really interesting. So keep an eye out for certified compilers. This one I think is probably my favorite component because I think we're going to see this very soon. I think, in fact, we've already seen quite a bit of minimal verified components. This is a small building block of software that is formally verified, and it's intended to just replace a chunk of code you've got in your critical low-level software project. So think like a parser or an encoder or a cryptographic function. These are all things that are known to have pretty significant bugs in them, or bugs with like really significant consequences. And they're also things that kind of have a standard API. Like of course, there are a lot of specifics to a parser, but I generally know that what goes in is unstructured text, and what comes out is some kind of structure that represents the text, right? Or I know that an encoder is following some mathematical formula laid out in a RFC somewhere. Same thing with a cryptographic formula. The nice thing about these is you can drop them into a standard library. You can replace the strings module in the C standard library with a formally verified alternative. and you've got the same API, and now you have a guarantee that the code you're running is going to do what it says it's supposed to do. I think it's already happening. I think it's going to become much more common, and at some point, people are going to make a name for it. I made up my own name, but I think this is going to be its own field of research, essentially in no time. So keep an eye out for that. And then I think when you've got these MVCs, when you've got enough of them, you can assemble them into their own standard library. You can have a completely formally verified C standard library, or Java standard library if you would want that for some reason. The nice thing about having a complete library is that I can take any of my C code, any big C project, any big C++ project, and I can pass in one compiler flag to swap the standard library that it uses. So don't use the GNU library, use my special formally verified library. And you basically automatically get adoption across millions of devices just by switching one little command line flag. Of course, there's a lot of effort that goes into this behind the scenes, but in terms of industry, they're not going to know that that's going on. So yeah, I think we're going to see our first verified standard library, I'm going to say within 15 years.
So you're talking about restructuring the basis of languages?
No, actually, this isn't restructuring languages or anything. This is just saying your C header files that you import when you write C.
Like the foundation of what we built our code on.
Yeah, just swap out all the functions for functions that we know are formally verified. And we can know that they're formally verified because we wrote them in a way that's very amenable to verification. Right now, if you go look at the source code for your pick of C standard library, there are several of them, you're going to notice that, number one, lots of it's written in assembly. Number two, the stuff that isn't written in assembly is so horribly optimized. And I say horribly as in like, it's very well optimized, but that means it's horrible to read. It's going to be horrible to read. If it's horrible to read, it's going to be horrible to reason about. And it's going to use these complex strategies. You can talk to anyone on my team. We've all done verification of C standard library code. It's ridiculous. But if I can write my own function, then I can write strcomp in the way that I think makes the most sense. And I can say that, oh, this makes the most obvious sense of why this is correct, which means I can write a proof very easily. And then I can give this to a certified compiler, which has optimizations in it that are proven to be correct. Ta-da, I've got a super fast, formally verified version of strcomp. Replace all of the string functions in your standard library with these formally verified versions, and ta-da, like you can just do this massive replacement for a minor hit in performance. So yeah, that's, I think, 15 years. Before 15 years, we'll see our first verified library. All right, so here we go, talking about hardware and AI. The reason they're bunched up together is that we can't really verify either of these things right now. You will hear about something called hardware verification. I'm here to tell you it's not what it sounds like. I would call it hardware validation. And generally, it's going to involve ensuring, do we know what, do we all know about Verilog and VHDL? Does anyone not know about those things? Okay, a few. These are languages, programming languages that have compilers where you write a program and it will generate a chip. It'll generate a chip layout, and so you can write hardware with a programming language. And generally, hardware verification is the task of ensuring that the output of the Verilog or VHDL compiler matches the input that you gave it. But it's not checking that like the Verilog you wrote actually does the thing you want it to do. That's like a completely separate question that, yes, people do, but it's not widespread, and for some reason they call this other thing hardware verification. So that's a problem. AI, I think it should, I hope it's pretty clear to everyone why you can't formally verify an artificial intelligence. It's because if I have 50 layers of a billion neurons and they're all just doing a matrix multiplication, how am I supposed to, as a human, how am I supposed to reason about why this model makes certain decisions in certain situations? It's just so ridiculously complex that there's no hope of it. So with the AI, I think we're just going to see a lot of external validation and more ensembling, where you have certain models that are extremely powerful but are less certain in their responses, and then you have several models that are not very powerful but very certain in their responses. And I think if you combine these in a specific way, you can get more trust in your AI. I think we're going to see this pop up a lot more, although stuff like that already happens, but I think it's going to happen more and more. And when it comes to hardware and input-output and device drivers and things like that, I made up this giant labs thing. That's Google, Intel, AMD, NVIDIA, and TSMC. These are all companies that, A, have buttloads of money, and B, they all have an interest in safe hardware. So we're going to see some conglomerate of companies come together and make a bunch of hardware specifications for chips that you have in your laptop right now. And when we have these hardware specifications, we can start combining them with software specifications. And we can know for certain that if we say that this chip, or if we prove that this chip is immune to speculative execution attacks, then I can know for certain that this piece of software that I wrote is safe and won't leak any user data. So that's what I think is going on there. This is the last one, last slide. So everyone turn off your science brain, turn on your science fiction brain, except probably most of you actually won't know why this is science fiction. That's okay. I wrote this for people who would know that it's science fiction. So all of this is going on. We see that formal methods is having this impact on cybersecurity. Industry is starting to adopt these methods because if all I have to do is swap out a compiler flag, that's free. It doesn't take me any refactoring time, really. So education is going to, again, increasingly readopt formal methods. We're going to see that governments are going to start mandating formal methods for critical software, not all software, but critical software. We actually see this a little bit. I do research on the formal timing behavior of binary code. So I can write a proof that says this piece of code is immune to timing side channel attacks or something like that. And the FAA already has requirements that you have to be certain that this autopilot software is not going to crash because there was a loop that took too long. So there are responsiveness requirements for code. So yeah, I think we're just going to see more of these mandates because things are going to be easier, so it's possible, so it'll become possible to mandate things. All right, this is the science fiction part. So raise your hand if you know what a loop invariant is. Okay, that's more people than I expected. Good. A loop invariant is a property of code. That's one thing already. It's just a property. The interesting thing about it is that a loop invariant is a property of code in the middle of its execution, usually at the point of a loop. And this property is true when you enter the loop, when you go around the loop any number of times, and then when you exit the loop. Don't really worry about why that has to be a thing. What you should know is that discovering loop invariants, as someone who writes proofs, is the hardest part of writing proofs. There is no formula for creating them. There is no pattern for creating them. There's no common properties of loop invariants that you could use to generate them. They're just really hard to come up with. And so I've proposed that in approximately 30 years, some grad student is going to discover some category of loop invariants or pieces of code that are verifiable with certain loop invariants in such a way that you can automate the generation of these. And that sounds very lackluster. I know it does. If we had a way to automatically decide the behavior of loops and the properties that are true when you exit a loop, it is literally impossible to overstate how ridiculously impactful that would be to cybersecurity. Because this whole time I've been talking about formal verification and proofs as being really hard and really time consuming, and it's expensive because you have to train someone to do it, whatever. If you could automate the creation of loop invariants, you could have formal verification be a part of your CI pipeline. So toss all the code into some Docker image that's running, have it step through all the code one time, infer the loop invariants, go through the proof checker. Ta-da. With no human input, you have formally verified a piece of code. And if you can automatically do it for one piece of code, you can automatically do it for a billion pieces of code. So if you could automatically determine the behavior of a loop, you could decimate software cyber attacks essentially overnight. So that's the science fiction of this, because unfortunately, the halting problem and Rice's theorem say that's impossible. That sucks. Actually, I mean, they say it's impossible for all loops, but that's why it's science fiction instead of fantasy, because it's only some loops that this grad student has figured out how to solve. So anyways, that's essentially my talk. That's it. That's the whole thing. I hope the thing I want to get across, I know all I talked about was the history and then the future, but what I want to tell you, or what I want you to walk out of here understanding, is that if you know the historical patterns of where money goes and where manpower goes and where education goes, you can predict where you should put your efforts right now to set yourself up for success 15 years from now when the academic solutions are mainstream. So yeah, that's it. That's all I've got. Does anyone have any questions?
Which company do I put all my stocks in?
About 90% of the stock I own is NVIDIA. And I've made good money on them. Okay, any other questions?
Is that financial advice?
Sure. Yeah, I'm just some guy. You can take whatever financial advice you want. I am a former NVIDIA employee, but they didn't hire me back, so I kind of have a grudge.
So does that mean you can get us free stocks?
No, not anymore. I don't work for them anymore.
But what if you know a guy that still works there?
I do know guys that still work there. I don't know why they would owe me anything, so I can't give anybody any free stock. Does anyone have any questions about the talk?
Can you explain loop invariance in more depth?
Yes, I can explain loop invariance in more depth. I don't have...
We get pizza first?
Yes, come get pizza. All right.